Today I'm going to give you a demo of our HEEDS design exploration software with a focus on the Simcenter 3D specific version of HEEDS. Now before I dive into the HEEDS product, I would like to briefly describe the Simcenter 3D simulation model that I'm going to use to set up the demo problem. So we have a static structural solution set up based on the geometry of a lower control arm. Our goal here is to find the lightweight design of the control arm that satisfy the constraints on maximum deflection and factor of safety. HEEDS will drive the geometry of the control arm by manipulating 15 geometric parameters that are defined in the control arm part file. Here is a screenshot of the finite element model of the control arm with the loads and boundary conditions shown. HEEDS will drive changes in the geometry of the control arm and it will automatically update the finite element model and execute the solution. Now let's take a look at HEEDS. So I have two versions of HEEDS up on my screen. The top one is the regular version of HEEDS and the bottom one is the Simcenter 3D specific version of HEEDS. Now regardless of what version of HEEDS you have, you will see this welcome info window. It shows you a schematic of the steps that we are going to deploy in HEEDS to build up a design exploration study. So the first step is creating your engineering design workflow. You will take your CAD and CAE tools and chain them up together in an automated fashion. You will then create a list of inputs or the variables that you want HEEDS to manipulate, and similarly you will create a list of outputs or the responses that you want HEEDS to monitor. You will map your variables and responses to your workflow. Then you will choose a type of study. You want to perform a parameter optimization, DOE, or evaluation sweep. You will then launch the design exploration study and HEEDS will look for the innovative solution using the hardware and the software resources that you have assigned. You will then use various post-processing tools to understand the data generated by HEEDS, look at the high-performing solution and understand why are they high-performing. Now each of the steps that is shown in this flowchart, they tie back into the tabs that are shown on the top left, that is process tab on the left through to the run tab on the right. So I'll begin by showing you the regular version of HEEDS and then I'll contrast it with the Simcenter 3D specific version of HEEDS so that you know the differences between the two and you can choose the correct version based on the workflow that you wish to drive. So in the regular version of HEEDS, you will notice a ribbon that shows you the list of various CAD and CAE tools. We have direct interfaces to all of these tools. We like to call them portals. A development effort goes into building this portal, and what they do is they make it very easy for the user to connect with the tool without having to know anything about the batch mode working of the tool. Now let me create a sample workflow to show you how easy it is to create a workflow in HEEDS. So let's say I'm building my CAD in NX, so I'll drag and drop NX. I'm doing my CFD in star CCM+, and let's say I'm using Simcenter 3D for evaluating my FE model. Now let's say that I have a costing model built in Excel and I wish to evaluate this costing model in order to know how much these design changes are going to cost me. Okay. So notice as soon as I click Excel, or as a matter of fact I click any of the analysis tool, I'll see these two gray bars. Now these gray bars tell me about the order of the execution of the workflow. The horizontal one tells me that my analysis tools will be executed from left to right, and the vertical bar tells me that my analysis tools will be executed simultaneously, that is in parallel. So if I drop Excel at the end, after all my analysis tools have been executed, Excel will be executed. If I move my Excel next to NXCAD, then the Excel analysis will be executed after NXCAD. So the position defines the order of execution. Now if I place my star CCM plus and Simcenter analysis vertically, then they will be executed simultaneously. Now if you notice that I have uplink tool, okay, so suppose you have some internal script or an internally developed code for which we don't have a direct portal, then you can use this general portal to drive those tools. Okay, now let me switch to the Simcenter 3D specific version of HEEDS. So the immediate difference that you will notice that you don't have a portals ribbon and you already have a Simcenter 3D analysis created for you. Now why that is? This is because Simcenter 3D specific version of HEEDS is meant only to drive Simcenter 3D simulation model. So suppose if you have a workflow that contains lots of analysis and consists of different CAD and CAE tools, then you should use the regular version of HEEDS. Otherwise, for driving Simcenter 3D models, Simcenter 3D specific version of HEEDS will be sufficient. So now I will switch to the Simcenter 3D specific version of HEEDS for the rest of it. So in this version of HEEDS, you can have only one Simcenter 3D analysis in a project, unlike the regular version of HEEDS where you can have many. Okay, so this is a direct portal to Simcenter 3D just as you have in the regular version of HEEDS. So HEEDS already knows how to execute Simcenter 3D, so the execution command are pre-filled for you. Now this brings us to the next step in building the design exploration study, that is adding the input and the output file. So the input file in case of Simcenter 3D will be the sim file. Now as soon as you attach the sim file, HEEDS will begin the process of parsing, that is reading the data from your simulation model. So all the expressions, physical properties and the solutions will be read. So this takes a minute or two to complete. So let's give it a few more seconds. So as soon as the process of parsing will complete, HEEDS will present you with two options. So the one option is to continue, that is create your variable and responses on the next parameters tab. The other option is for creating the variables and responses and the mapping to your simulation model right away. So we can do this by choosing auto tag. So tagging is basically the process of connecting your variables and responses to your simulation model. So let's create some variables. So if you see that HEEDS has nicely organized the expressions based on the files in which they exist. So you have your CAD expressions in the part file, they are organized under CAD expressions. Similarly, you have FEM expressions and you have expressions defined in your simulation file. So let's create some variable out of CAD expressions. Okay, so this is the name of the part file. So for creating the variables out of expressions, all you have to do is to check the box next to the expression name. Okay, so if you see that HEEDS has already created variables with the same name. Now by default, HEEDS creates variables of continuous type. That means you have to define a min and a max value, and HEEDS has already picked up the baseline value from your component files of a simulation model. So in this case, the part file. So let's define ranges. So HEEDS will pick up the value between this min and max to design this particular variable, and then I'll quickly define the min and the max value to complete the definition. So after defining the variable, it's time to create responses. Okay, so HEEDS have extracted expression, physical properties and solutions. So I wish to monitor the mass of the control arm and the displacement. Okay, now notice one more thing, that HEEDS already detects and picks up the component files of a simulation model. So in this case, the FEM file and the part file, and on the output side we have the same file because all the solutions are saved in the same file. Now by default, you can execute this analysis on a local machine, but it doesn't have to be like that. You can use a different hardware resource to execute this analysis. How do you do that? You choose the hardware resources from this drop down, and assign it, and your analysis will be executed on the chosen hardware resource. Now in this case, scheduled 1 is a cluster in my office that I use regularly. You have to define one time the configuration, and then you can use in all your projects. Okay, we have other options available for the Simcenter 3D portal. So you have solutions, so you can check the solution you want to execute. Okay, if you have several solutions, you can skip the ones you don't want by unchecking the box. Then you can choose to save or not save the modified simulation model. One nice thing about the Simcenter 3D portal is that it will extract the images associated with your layout states if you have created any in your simulation file. We have provided a space for specifying any additional macro that you may want to do for doing some post-processing that requires the use of the UI. Okay. You can also choose to export your CAD models in these formats if you'd like. So under the Wiz tab, you will have all the images associated with the layout state that are automatically added. Okay, so now the next step is to move on to the parameter. The parameter tab is exactly the same as you would find in the regular version of HEEDS. Now if you see that whatever variables we created in the AutoDAC, they are already added to this variables sub-tab, but I can modify the name, type, and variables, ranges, anything I want here too. And also I can add more variables. So let me add few more variables. Okay, so let me give some name. So here I'll give some name to the variables. Let's say radius. Length. So by default, the variables created are of continuous type. Now, due to the manufacturing processes, you may want your thickness to be of discrete type and not continuous. So what discrete type of variables are? They are basically the list of discrete values or specific values that you want HEEDS to pick up. So what you can do is, you can go to the sets, you can create a set, you can add as many values as you want. So let me add some values, and I want HEEDS to only use these values. So I'll assign this set, and HEEDS will only use these three values, one of these three values to design thickness. Okay. Now you can create variables of dependent type. So that means if you have any relationship or condition to uphold or define among the variables, you can do that. So in this case, I want my radius to be 3 times my, let's say, arm extension. Okay, you can type in manually or you can pick it up from these menu. Now this is a Python based calculator, so that means whatever you can write in Python script, you can write here too, and it will be executed. So we have functions available. You can write your own. So let's say if you have some conditional statement or you have loops, you can include here and it will be executed just as would have been executed through a Python script. Now variables can be of constant type. So just as the name implies, this will hold the value of a variable fixed. So let's say you are in a stage of your design process where you want to look at your manufacturing tolerances. So you can give it a fixed value to the constant type variable and then define the distribution matching what you can manufacture, and you can study the robustness of your design. Okay, so let's move on to the responses sub-tab. Here again you will see that 2 responses that we created using AutoDAC are already here. So by default, responses are created of tag type. That means that somewhere in the output file we have created, or we have put a stamp on a location, and HEEDS knows that it has to go in that location and extract the values. Okay, so in the next tagging tab I'll show you actually how it's done. You can create additional responses if you'd like here too. So let me create few additional responses. Let's say I want to monitor stress, so I'll create max stress. I want to calculate factor of safety, and let's say I'm doing some vibroacoustic analysis, so let's say I have acoustic power as one of my responses. Okay, so by default, as I told you, it was tag type. You can create responses as a formula type. That means again it's the same calculator that we just saw on the variables subtab. So let's say I want to calculate factor of safety. I know 250 is the yield stress of the material that I have, and divide by the max stress. Okay, then you can create responses of curve fit type. That means if you have any experimental data or any set of data and you want to tune your simulation model, then you can create responses of curve fit type. Now we have various other responses available. We have variety of filters available. We have forming limit diagram for solving the sheet metal problems, as well as you can operate on response surfaces. Okay, so at this point of time, the newly created variables and responses have no connection to the simulation model whatsoever. The ones we create in auto tag, they're already connected, but the newly created one have no connection. So we are going to create that connection in the tagging. So to create the tags for a variable, what we'll do is you will pull the input file, in this case the sim file with the green arrow, and as soon as we'll pull the input file, you will see that your some of the variable tags have already been created. This is what we created using the auto tag feature. Now to tag the newly created variables, what you will do is you will choose the variable from the drop down, and then you will scroll down to the expression that you want to drive using this variable. So let's say I want to drive web thickness tag. So similarly I can tag radius. Okay, so it's we can select radius and then tag radius. So this is how you create variables. Now for creating the tags for responses, you will select the output file, that is a sim file with the blue arrow, and then you will see that already the responses have been created. These are the ones we created in the auto tag. So this is mass and this is displacement. I can modify the definition of my displacement response. So let's say I want to just extract the max value of displacement instead of nodal displacement for all the nodes in my computation domain. So I can just say max. Okay, so for creating additional response tag, you select the tag, in this case max stress, then go to the max stress. In this case I want to tag the von Mises stress, get the max value, just click tag. Okay, now we have created the variable tag and the responses tags. Now one thing to note about the Simcenter 3D specific version of HEEDS, that you can only create variables and response tags based on the data that is read by the Simcenter 3D portal. So if you have an ASCII based file like a text file or a CSV file, you cannot use them to create tags. That is, you cannot use them to drive changes or extract responses from. Okay, so at this point we have completely defined a process automation. Now HEEDS knows what to execute, where to execute. HEEDS knows what to change, what to extract, and how to do that. Okay, now the next step is to define our. So the study tab is exactly the same as you would find in the regular version of HEEDS. So here under the study tab, the first step is to choose the type of study you want. So you want to do a parameter optimization, DOE, robustness and reliability, or evaluation only study. All these are available within one license of HEEDS. You will use one algorithm, that is Sherpa. The only decision that you have to make while setting up a design exploration study in HEEDS is number of evaluations. So let's say that I know my simulation takes 1 hour to complete. So, and I have 3 days. So what I can do is I can allow 72 evaluations. Now HEEDS will do its best to find solutions, innovative solutions, the best solution within 72 evaluations. Now let's say my production deadline has been pushed and I can do a more exploratory search. So I can increase this number. Now I can still do an exploratory search while spend less time. How can I do this? HEEDS has a very nice feature called HEEDS Parallel, where you can achieve linear speed up by evaluating multiple designs simultaneously. So I can give it a number. So it will give me a 4-time linear speed up. I can increase the number, whatever your hardware and software resources allow. Okay. Now, once you have done this, you can now define your optimization statement. So in this case, I'm looking to minimize my mass, and I want to maintain my displacement below 0.5 and my factor of safety above 1.5. Okay, so I have completely defined my design exploration study. Now I can go to the Run tab and click Run, launch the design exploration study, and HEEDS will find innovative solution for you using the hardware and the software resources that you have assigned. I've already completed running the design exploration study in order to save time on this demo. So let me load the completed project. So I want to mention that whatever features or steps I'm going to show from here on will be the same as if we were in the regular version of HEEDS. Okay, so in total we did 400 design evaluations, and here is a breakdown that you see. So 48% of the designs for the feasible designs, that means they satisfied all of the constraints, and 33% were the infeasible designs. That means that they didn't satisfy at least one of the constraints, and then rest for the error designs. Now, why a design would error out? Now, there can be several reasons, like the CAD didn't regenerate, or the mesh regeneration failed, or the solution diverged. The important thing to note is that HEEDS handles these error designs very efficiently. It kind of puts an asterisk next to this design and then moves on with the further design evaluation. One nice feature of the Simcenter 3D portal is that it captures messages from Simcenter 3D, so that you can quickly diagnose why did your design error out. So you have to go to messages, then analysis, Simcenter 3D, and then you can select a design with a cross. So this cross represents an error in design. So you have to click on this hyperlink, and it will open a show your messages in a text editor. So here you see that it says that the CAD update failed. So input parameters may not be feasible. That means the variable combination selected by HEEDS didn't result in a valid CAD. Okay. Now let's dive into the post processor, that is HEEDS post, and see what we can learn about a design statement. So first is the objective history plot. Each dot on this plot represents a design point. Okay, so the blue ones are the feasible ones, the red ones are the infeasible ones. The solid blue line shows you how HEEDS went about searching your design space. On the y-axis, we have our objective, that is mass. Our aim is to reduce the mass, that is come down on y-axis, and on the x-axis, we have the design evaluation number, or called design ID. So he started off with a infeasible design with a mass of 4.15 kg, and just below 50th iteration, he's found a feasible solution with reduced mass, and then it continued to reduce the mass and find its last best solution at 300th iteration, which is about 3.62 kg, and that translates to 13% of the mass saving over the baseline. Okay, so as discussed, he captures images from your simulation model. So these are the CAD images. These are captured regardless you have created layout states or not. So you can look for images for each design by using these arrows, or even you can use these slider bars to view images for each design. These are the images associated with layout states. You can view images using arrow, and these are the displacement, and this is stress. So HEEDS captures data for each design it has evaluated. So if I go to the design table, then you would see the data for each design, and you can sort the design based on any parameter you'd like. So if you click on the top, it will sort the values based on flange width, or maybe cut out inset, and you can sort the design table using the rank. Okay, so this puts your high performing solution on the top, and what you can do is you can create a design set of the high performing solution if you would like to study the trends later, why they are high performing, and you can create the design set using this context menu. Okay, then whatever plots that you want to use in post processing, they are all conveniently located under the create plot menu. Okay, so one such plot is the 2D relation plot. Okay, so here what we see is a feasible design set, so I can choose a design set whatever I want to plot from here. Some are created by HEEDS, and you can also create the design sets. So on the y-axis we have factor of safety, on the x-axis we have maximum deflection. You can overlay design points with the color. So in this case the color represents my mass value, and the size represents my web thickness value, so I can choose any. So what do we see from this plot is, if you look at the color, moving to the right, the mass is decreasing, mass is decreasing, and max deflection is increasing, and also the factor of safety is decreasing. And the same trend is being followed by web thickness. Looking at the size, we can see that as the size is decreasing, the maximum deflection is increasing, and the factor of safety is reducing. Okay, so let's see if I see this is a design set for my top 20 designs, and what do I see in here is my best design has a mass of 3.62 kg and factor of 1.56. While looking at the color, I can see that okay, the mass looks similar, and let's find out what that is. Yeah, the mass is 3.62 kg, but it has a slightly higher factor of safety. So this can be a good candidate since it has similar mass but has a better factor of safety value. Once you have created this plot, you can view them now on a single window using plot views. So in plot views, the plots are synchronized. So if I select a particular design point here, I'll see the corresponding images as well as the same design combination on the other plot. So on top, what you see, it's a parallel plot. In a parallel plot, a design is represented by a line. On the x-axis, we have the parameter name, and on the vertical axis, we have the parameter range that was explored by HEEDS. So let's similarly look at a best design. Now let's see why, what's the difference between the best design and the other high performing solution that we identified. So I'll click Control and select my other high performing solution. Now I see that most part for the most part, both of the designs are same. There's a difference in factor of safety, and if we see on the variable side, that is on the CAD parameter side, we see that except rib thickness, all the other CAD parameters are same. So here rib thickness is causing the difference in the factor of safety. So this was a quick demo to show you that HEEDS not only finds innovative solutions for you, but also helps you to understand why they exist and provides you with intelligent information to make design decisions.